Swayam Prabha. Digital India. Educated India.
We will continue from where we left off in the last class. In the previous class, what we did is we spoke about the problem of a thin film flowing down a wall because of gravity, okay, and we saw that the pressure was uniform everywhere, and the gravity forces were being balanced by the shear stress forces, and we did both the microscopic balance, which is the differential equation, and the macroscopic balance, where we looked at the control volume and saw that the gravity was being balanced by the shear stresses. Okay. So, this is the falling film. We had gravity forces balanced by the viscous forces, the microscopic level. What I mean by that is the differential equation. So, when you look at the differential equation, you had rho g and you had the viscous forces. Those are the only two terms remaining, okay. And at the macroscopic level, that is, we took a control volume and did a force balance. Here the gravity balanced the shear stress on the wall. Okay. Shear stress is coming basically because of viscous force. Okay. Shear stress at the wall is tau times mu times the gradient of velocity. So, that was the macroscopic version. So, all I am trying to tell you is that the forces were being balanced, because of which there was no acceleration, and that is the reason all the velocities were uniform. The velocity of the part did not change as you moved down the film. Okay. So, there was no acceleration in the system. Okay. And h was constant, velocity was constant. H, the film thickness, and the velocity could all be constant. I mean, this is possible, but this is the problem we saw in the towards the end. I mean, so the differential equation is valid at every point, and so I say that is the microscopic balance. You have the mu d square v by dy squared or x squared, something like that, equal to rho g. Okay. Then you did the integration over the control volume and you got the exact balance. The gravity force acting on that control volume is balanced by the shear stress. Suppose now you have a jet of water falling down. That is, you open a tap, okay, and When you open a tap, you see water is going to come down. Now, so this is the tap opening, okay, and there is water coming down, Now, as the jet of water comes down, it is going to accelerate because of gravity. In this particular problem, there is no wall, the entire surface, let us assume that this jet is cylindrical, the entire surface is exposed to air, and the gas liquid interface has zero shear stress, there is no shear stress, okay, because the viscosity of the gas is very low, there is absolutely no shear stress. So, there is nothing to oppose the motion, only gravity is going to be acting downwards. In the previous problem of the jet on the wall, we had the wall surface giving the shear stress. Here there is nothing which is going to prevent the, nothing acting to counter the gravity. So, gravity is the only force acting downwards. So, what that means is this force is not going to be balanced, which means that the liquid is going to accelerate, all the particles in the liquid, the liquid will start accelerating. And it is like your solid ball, I mean you leave it at zero velocity, it is going to accelerate as it comes down because of gravity, okay. So, here the liquid jet is going to accelerate, so as the velocity keeps increasing, what is going to happen? Because of continuity, the area of the cross section through which is flowing will decrease. So, it is going to become thinner and thinner and thinner, okay. So, I am going to draw this slightly bigger. So, you understand this is a really big jet, but this is just for your clarity. It is going to become thinner and thinner and thinner, eventually it will break into drops, okay. So, this is the jet of water, gravity is acting downwards, the velocity keeps increasing, this is the direction of gravity, okay. The velocity keeps increasing, the cross section of the jet decreases due to continuity, there is zero shear stress at the walls, and hence no viscous stress opposing the flow. Hence, so the liquid accelerates, okay. So, there is a fundamental difference between these two problems. Now, when you look at this second problem, okay, this is the actual situation, and as it becomes slower, smaller and smaller, as the cross sectional area becomes smaller and smaller, the surface tension effects will dominate and the liquid will break into drops. If you wait for a sufficiently long time, you might have seen that if you open the tap in your bathroom very slowly, I mean the liquid will come in the form of some jet will come, then it will break into drops, okay. But if it is very high, it needs to go a longer distance before it breaks into drops. So, here basically surface tension effects become important, here it is still not dominant, okay. So, this drops are formed when the surface tension dominates, okay. Now, suppose the jet does not accelerate. I mean, supposing you are doing this experiment in outer space where there is no gravity, okay. So, then the jet will be having a constant cross section, okay. The cross section is uniform. Say jet is in space where there is no gravity. Okay. Then this is the axis, this is r equals r naught. So, the surface of the sphere is defined as r equal to r naught, which is constant, r equal to constant, r naught is constant, okay. This is constant. So, I call this this is an iso surface, because one of the coordinates is constant, r is constant, okay, iso coordinate, okay. So, basically what I am saying is the surface here is very simple to define, r equal to constant, r naught. In the second problem or the first problem that we discussed, the jet is symmetric still, it is falling down. Here surface is not a constant, r is going to be a function of z, okay. So, this is, let us say z, or make it downwards, surface is defined as r equals f of z. So, it is not a constant surface anymore, okay, because every z the location of the surface is different. So, this is r equal to f of z is a surface. Now, what is the fundamental difference between these two problems? Here the outward normal n to the surface is in the radial direction, okay. What about this surface here? The outward normal in this system is neither in the radial direction nor in the z direction, okay. So, the outward normal has both ER and EZ components. So, this is the outward normal, this has both ER, EZ components, and the normal is going to keep changing with z, because the curvature will keep changing. The normal here will be different from the normal here, will be different from the normal here, okay. The normal here is pointed in this direction, the normal here is pointing in this direction, things like that. The normal keeps changing, normal is also a function of z, okay. So, what we want to do is we want to understand, because when you have a surface of this kind, you want to be able to apply the boundary conditions at the surface. See, whenever you are solving a problem, you need to apply boundary conditions. These boundary conditions have to be applied at that surface, okay. And this is one of the areas where our formulation of n dot t. So, what will be the stress, how will you find the force on this thing? You have the stress vector, n dot t gives you the stress vector, okay. So, we spoke about using n dot t to convert the surface integral to the volume integral, and then we got the differential equation. I am saying this n dot t concept is useful here also when I am going to apply boundary conditions. When I apply boundary conditions, I will be doing a saying the tangential stress is 0. I am going to put conditions on the normal stress, okay. So, my boundary conditions are formulated physically on the basis of the normal stress and the tangential stress. Okay. So, we need to basically use this n dot t to find out what are the stresses in the tangential in the normal direction. So, you have n dot t. What does this tell you? It tells you the stress vector, the force components per unit area which are acting on a surface whose outward normal is in the n direction. That is what we said earlier. Okay. This tells the, maybe I put tau last time, tells the stress vector or all the components acting on a surface whose normal is n. Okay. And now I want to further resolve it. In, so this n dot t tells me the force which is acting. This force will have different components in the normal direction, tangential, any direction you want, you can resolve it. How do you find the component along a particular direction? By taking a dot product with that direction. Okay. So, n dot t dot n. So, this is the force, I am dotting it in the normal direction. One more, so n dot t is a vector. Okay. That is why I wrote stress vector. I dotted in the normal direction to get the component in the normal direction. Gives the force or component in the normal direction, and n dot t gives the force component in the tangential direction. Okay. So, n dot t is the force acting on a surface whose normal is n. I dot again with n, I get the normal stress component, n dot t gives me the component in the tangential direction. So, that is basically what I need to do. I need to find this, and the boundary condition I will have for this gas liquid interface will be, so on the jet surface I have to put n dot t equal to 0. This is my 0 shear stress condition. The tangential stresses are 0 because gas does not give me anything. So, what we are going to do now, so I started with the motivation with the cylindrical coordinate system, but since we have not started cylindrical coordinate yet, I will just explain these concepts with the rectangular Cartesian coordinates, and then we will come back to cylindrical coordinates after that. Okay. So, I do not want to introduce two things at the same time, cylindrical and this concept of how to find this. So, let us do consider an analogous problem. Consider an analogous problem in the rectangular Cartesian coordinates x, y, z. Okay. Okay, we will do cylindrical after this. So, now, so this is x, this is y direction, and let us say this is the surface. Okay, this is the liquid, and we will keep life simple, make this gas on top. So, and the surface, like suppose you go to the beach, you will see that the surface keeps varying with space and also with time. Okay. So, this surface f is a function of x and t. Okay, like standing on the beach, you see the waves which keep coming on the free surface. And now the question is, I mean, what are the questions we are going to ask? I mean, how do you track what are the conditions which are going to apply? How do you find, how does the interface change? And we are going to find out how does the, how are the boundary conditions going to be applied? Okay. So, how does the interface change, number 1, and what about boundary conditions on the surface? You remember, I mean, so the surface now is going to be defined as, surface here is y equals f of x comma t. So, one coordinate, another depends on the other coordinate. Similar to r is equal to f of z. Okay. In the earlier problem, what I said, this is analogous to r equals f of z comma t. I am putting a t also there now. What we saw earlier for the jet problem. So, this is like my r, this is like my z. Okay. This is for the jet. But I am going to Cartesian because I think it is easy for you to visualize things. Okay. Then mathematically we will extend to cylindrical. Y is equal to f of x comma t. I am going to write this as, this is the explicit representation of the surface, where one coordinate is explicitly being represented in terms of the other. Okay. An implicit representation will be f of x comma y comma t equals y minus f of x comma t. This is the implicit representation, okay, equal to 0. So, capital F is just an implicit way of representing the surface, and small f is the explicit representation. So, the way I have defined capital F, it is going to be 0 for all times t, right. On the surface, capital F will always be 0 because I have defined it as y is equal to small f of x comma t. So, it does not matter, f of f can be different. So, for all times t, for all t, capital F is 0, okay, by definition, because capital F is y minus f, surface is y is equal to f. So, y minus f will always be 0. So, I go from one time instant to another time instant, f is going to not change, f, capital F will be same, capital F will always be 0. So, what I mean by that is df by dt equal to 0 for all t. And if you remember the derivation which we had, a particle on the surface is always going to satisfy f equal to 0. I am going to do what we did earlier, write it, this is like the Lagrangian representation, I will write it in terms of the Eulerian representation, okay. So, df by dt is nothing but df by dt plus v dotted gradient of f. Okay. So, on the surface f does not change with time at all. So, the total derivative, the material derivative, the Lagrangian derivative is 0, but all I am doing is using this definition which we saw earlier when we related Lagrangian to Eulerian. Okay. Now, I can substitute for f here, what do I get? What is capital df by dt? The partial, this is independent of time, only small f is dependent on time. So, this is minus df by dt. okay, plus the velocity vector, I can write it as u is x component of velocity, gradient of f will be u df by dx plus v df by dy, okay. All I am doing is expanding gradient of f like df by dx and then doing a dot product. By now you guys are experts. So what does this give you? So this tells me minus df by dt plus u, what is df by dx? Capital df by dx is, I am doing the partial derivative with respect to x. So y is constant, t is constant. So it is a minus df by dx, minus small df by dx, okay. There is no dot here, huh? Plus v, what is df by dy? df by dy is 1 equal to 0. So basically it tells me v equals df by dt plus u df by dx. So if you want to find out how small f changes with time, supposing you have a problem where the interface is changing with time and you want to track the interface, like I talked about the wave, the interface keeps changing with time. So there are some forces acting on it. So what is the equation which tells you how does small f, okay, the surface change with time? This is the equation which relates small f, and this is called the kinematic boundary condition. Okay. Supposing you have a system where small f does not change with x, okay. If small f is independent of x, v equals df by dt. So, you know, you have a bucket, you are filling it with water, the level in the bucket goes up, okay. So all I am saying is df by dt, the rate at which it is going up is equal to the velocity, okay. That is what we expect, right. I mean the rate at which the surface is increasing with time is going to be equal to the velocity. That is what this means. So that is basically just to tell you how to interpret this boundary condition physically in a simple case, like when f is not a function of time, not a function of x. So point is, when you do a derivation and you come up with some results, you have to make sure that the derivation you have done is right by looking at some simple cases like this, the limit of what happens if it is not a function of x, what happens if it is not a function of time. Supposing it is not a function of time, if f is not a function of time, if f is independent of time, okay, what do you get? df by dx is equal to v by u. So df by dx is the slope, okay, df by dx is the slope, and basically the slope on the surface is going to be given by the ratio of the velocities, the v and the y, because on the surface the velocity is going to be tangential. So this has two components, vertical component and the horizontal component, okay. So basically this is the slope of the surface, okay, and now the surface is not changing with respect to time. You have some surface, that means what? The liquid is moving in that direction. So v and u, the velocity components, are exactly tangential to the surface. That makes sense, okay. So point is, I mean, you have to learn to think about the problem not just mathematically but also physically to understand whether what you have done is right, okay. So look at any problem using two perspectives, Okay. So, this is how I track the interface. Okay. Now, I need to talk about how do I find the boundary conditions, how do I apply boundary conditions on the interface. Okay. And kinematic boundary condition is used to track the interface. Okay. Now, we need to apply boundary conditions. So, for that, first thing I need to do is find the normal, right. Only then I can do n dot t and all that. So, my surface now is f of x comma y comma t, which is y minus f of x comma t. So, when it comes to boundary condition, I am going to be applying the boundary condition at every time instant. Okay. So, I am going to basically you will be fixing a particular time, at every time the boundary condition has to be valid. So, time is fixed, okay, at every time you apply the boundary condition. So, although the surface may be changing, so the capital F will become the small f will become different, but capital F remains the same. So, now, so this is your boundary f equal to 0. How do you find the normal? And you must have done this in one of your math courses, and that time possibly you never had any idea where it was going to be used. Okay. The normal is defined as gradient of f, and if it is a unit normal, you divide it by the modulus of gradient of f. Okay. This is gradient of f divided by the norm or the modulus of gradient of f, because I want to get unit normal. It is like what you did in your math course where you normalize the vector. Okay. So, here what is gradient of f going to be? Grad f is Ex d by dx plus Ey d by dy, and this is the reason I came to Cartesian coordinates, because I can deal with xy rather than go to r theta, not dotted f. There is no dot product here, okay, it is just gradient, f is a scalar, capital F is a scalar. So, what is this going to be? Ex, what is partial derivative of f with respect to x? Partial derivative means everything else is constant. So, it's minus d f by dx, okay. This is minus f of x plus Ey, what is d by dy? 1, okay. So, basically I am saying this is Ey minus f dash Ex, f dash is df by dx, okay. So, that is gradient of f. So, what will be the normal? Normal will be divided by the magnitude okay, because now this has unit length, okay. So, all I have done is, so the grad f concept and this implicit representation helps me find the normal derivative, I mean the normal, okay, direction to a surface. How do you find the tangential direction? The tangent has to be perpendicular to this, the normal, and then you have the tangent. So, I mean you can do it any which way you want, but because this is a simple problem in 2 dimensions, again what I really should do is look at why the function of x, z and t, there is also a z, okay. Now, z I am not considering, because I am saying nothing is changing in the z direction, I am just focusing my attention on 2 dimensional problem, okay. So, keep in mind that I am saying nothing is changing in the z direction, like in the z direction things are going to infinity. So, no changes in the z direction. That is an assumption I made. Otherwise, you have to consider f of x comma z comma t. Okay. Just to keep the mathematics simple and explain physically, I have not considered the z dependency. Okay. The tangent is going to be perpendicular to this. So, I am going to say it is going to be equal to f dash E y plus E x divided by square root of 1 plus f dash squared, right. I put f dash here and plus sign here, you take the dot product of these two, n dot t has to be 0, okay. I am just looking at it because the 2D problem I can do it easily, n dot t must be 0 because n and t are perpendicular. Okay, because it is a straightforward problem in 2 dimensions, I just did it by observation, but otherwise you can do it mathematically. Okay. So, now I found the normal direction and I found the tangential direction. I need to calculate the shear stress on the surface where f is changing with x. Okay. How to find the shear stress on the surface? For that I do n dot t dot t. Now you can do it any which way you want, okay, either write everything in terms of Ex Ey and expand it, or you can do matrix formulation, both should give you the same result, okay. But I am going to keep it simple, n is the unit vector in the normal direction, so it is minus f dash. So, actually it is a 3-dimensional problem, okay, but because I have assumed z to be infinity, I only am worrying about x and y. So, the problem is essentially 2-dimensional now, okay, because I am neglecting all changes in the z direction. So, I do not care, nothing is changing in the z direction. So, why waste our time talking about z? Only x and y is of interest to us, okay. So, that is what we are doing. And so, what I am trying to tell you is, we do not worry about z. So, n also has only 2 components, Ex Ey, t has Ex Ey. The stress tensor to capital T will also have only x and y. It is not going to be a 3 by 3 matrix, it is going to be a 2 by 2 matrix, okay. Other elements will be 0, so let us not waste our time. So, basically n is going to be, this is, I need a scalar at the end of the day. So, 1 by 2, this is 2 by 2 and this 2 by 1. So, I am going to write the n as a 1 by 2, okay, because it is much easier for me, 1 row 2 columns, 1 row 2 columns, first is x, so minus f dash 1, okay. The stress vector T is written as tau xx, tau xy, tau yx, tau yy, and small t is, I already found small t, which is 1 and f dash, okay. So, what x is my first direction, so that is my first component. You can also do the same thing using the Ei Ej, what we discussed earlier, okay, and you should get the same result. But I think this is much easier for me, so, and maybe for you also, so you can do this, this matrix multiplication. I told you matrix multiplication and this Ei Ej should give you the same result, okay. So, you multiply this matrix and you will get a scalar at the end of the day. What I have not done is, I have forgotten the square root, okay. There is going to be a square root of 1 plus f dash squared coming from here, there is a square root of 1 plus f dash squared coming from here. So, there is going to be a 1 by 1 plus f dash squared, okay, because I have normalized everything. So, can you, so I am going to take the product of these two first and then of these two, whatever I get, and I will get my result. Okay. So, this must be equal to 0. This equal to 0 is my boundary condition. Okay. So, the idea is on the surface the shear stress is 0, the tangential stress is 0. This is the tangential stress component. N dot T tells me the full component, N dot T tells me the tangential component, this must be 0. Okay. So, the boundary condition which I am going to use is, I have to evaluate this and put it equal to 0. Okay. Do the matrix multiplication and you can check if what I am doing is right. So, I have 1 by 1 plus f dash squared. It does not really matter what this denominator is, only the numerator matters, because if this is equal to 0, the denominator does not bother me. So, I will just put the numerator equal to 0. Okay. So, I do not need to really write the denominator. How do you do this, man? I forward this thing. Minus f dash tau xx plus tau yx okay, and that is my first term. When I do this multiplication, this row first, f dash multiplies tau, 1 multiplies this, I get this, f dash multiplies tau xy plus tau yy. So, this is one element, this is another element, okay. Just to be on the safe side, I am putting a bracket here, and this multiplies 1 f dash. X is my first component, so that is the first component here. Okay. X is my direction 1, y is direction 2. So, x is the first element, coefficient of this is 1, coefficient of this is f dash, and this is the tangential direction, this is the tangent. Okay. Again, do this matrix multiplication. Like I said, the denominator does not matter. So, I get minus f dash tau xx plus tau yx minus f dash squared tau xy plus f dash tau yy equals 0. All I am doing is multiplying this. Okay. Again I repeat, you do EI, EJ, do the same thing, you should get the same result. I is 1 is x this. So, this is the boundary condition which you have to use. How do I check? I mean that I have not made a mistake, or it's likely that what I have done is right. I should look at some case which I already know. What case do I know? When f does not change with x. Okay. If f is independent of x, that is y is equal to constant, right. F of x means it is changing with x, it does not change with x, that means y is constant. Then what happens? F dash is 0. If f dash is 0, that goes to 0, 0, 0, and have tau yx equals 0. Okay, and that is basically what you expect, because if the surface is flat, tau yx is, y is the normal direction and x is the tangential direction. Okay. For this case, this f of x, this is constant, this is y equal to constant, this is the normal direction and this is the tangential direction. Agreed. Now, the interface is flat, the normal is in the y direction, the tangent is in the x direction, and we said tangential stress should be 0. So, now it should be tau yx, the first subscript tells you the direction of the outward normal, second subscript tells you the direction of the stress. So, tau yx is 0, which is what you expect for a free surface. Okay. So, most probably what I have done is right. It could be I made some mistake somewhere and may be wrong, but you have to check that. Okay. For a plus sign, minus sign, anything could be wrong. okay, but I don't think there is anything wrong here. So, this is a generalization of the boundary condition for f which does not, f which changes with x, okay. You can do the same thing for the normal stress component, but now instead of T you have to use N, okay, and get the normal stress component, and this will now be in the normal stress component, this will become minus f dash 1 and expand it the same way. I am not going to do it, okay. So, similarly you can find normal stress component, we can find n dot t dot n, okay. The third vector will now be n, not small t, okay. So, this is just to tell you that small n dot capital T has applications in formulating boundary conditions in a general sense, okay, and this is how you would use it. What I want to do next is talk about cylindrical coordinates, and we will do that in the next class, but I told this earlier also. One of the characteristic features of cylindrical coordinates is when you change the one of the coordinates, the unit vectors can change, okay. So, the derivatives of the unit vectors, especially in the theta direction, is non-zero, and when you use that, incorporate that, then you get the Navier-Stokes equations in the cylindrical coordinates, the equation of continuity and the Navier-Stokes equations. You get extra terms. So, as opposed to what you would get in the Cartesian coordinates. In the Cartesian coordinates you do not get extra terms, but because of this derivative variation in the theta direction, the derivative not being 0, when you derive the Navier-Stokes equations, when you derive the equation of continuity for spherical and cylindrical, you will get additional terms, okay. That is what we are going to see next.